Hello, welcome to another Midnight Maths video. In this one, we are going to cover trigonometric substitution. So we're gonna go over like a quick process for picking a substitution and so on. And we're gonna be using this as our example today. So let's get started. So the first question here that we have to ask ourselves is, do you even trig sub? Because trig sub is quite a lengthy and annoying method to use. So if you can use something else like u sub or partial fractions, that'll usually be faster, right? But there are some cues for trig sub, and the biggest one is one of these forms. We have x squared plus a squared, x squared minus a squared, or a squared minus x squared, where a is an arbitrary number, like 3, or 4, or something. So if you see one of these forms, it's an indication that you might be able to use trig sub. A lot of times some of these forms just can't be factored out, so you can't use partial fractions or something like that. So now that you've identified that you may need to use trig sub, the next step would then be to pick a substitution. So there are, like, the idea basically, right, is we're gonna make x equal to a, that same number, times some trigonometric function of theta. And with this, we have two options here with f of theta. So it's going to either be a sine, a tangent, or a secant. And these three categories really come from Pythagorean identities. So there's this one, right? And then there is this identity here. Tangent squared plus 1 equals secant squared theta. So these two are the primary two that you use in trig sub to simplify things. So we have, like, for example, what we do is we identify which one of the forms. So here we have x squared plus a squared. And then we sort of write it in that form. So we want it in root x squared plus 3 squared, right? Because that's what we see up here. So we're just going to use that. We're going to use that down here. Okay, so we have this. And now, if you don't quite know which trigonometric function to use, you could just plug in this general form because you know that it's going to be of that form. So, we end up getting root 3, because a is 3 in this case, f of theta squared plus 3 squared, and then we're going to get a root 3 squared f theta squared plus 1, right? After we factor out a 3 squared from there. And this is going to give us 3 times root f of theta squared plus 1. So now we want to simplify this radical and ultimately get rid of it. So how does that happen? Well, this whole thing has to be something squared, right? Like if you have root 2 squared, then that just becomes 2, and that's good. So we compare this part, this f of theta squared plus 1, to our Pythagorean identities up here, and then we decide which f of theta would fit in the Pythagorean identity. So in this case, I see a tangent squared plus 1, right? That's f of theta squared plus 1, where f of theta is going to be tangent theta. And then we know that if we pick, based on this identity up here, that if we pick f of theta equals tangent theta, then this right here will simplify down, because I have tangent squared theta plus 1, and then that's going to be secant squared theta, so you're going to get 3 root secant squared theta. Now, this is going to technically be absolute value secant theta, but since we're dealing with indefinite integrals here, we usually just sort of ignore the absolute value bars and implicitly put a restriction on theta. In definite integrals, though, the domain restrictions and what exactly you're doing starts to matter more. So I'll explain more in another video where we do a definite trig subintegral. So for now, we know that our substitution, because we found out f of theta is tangent theta, so then our substitution up here, we know that x equals af of theta. So finally, our substitution is going to be, right, we're going to copy that. Our substitution is going to be x equals 3 tangent theta. Okay, good. And then we also know what our radical simplifies down to. So this was our problem right here. And we are going to write this as in the same form, right? So 1 over root x squared plus 3 squared dx. And now we know we apply the substitution. That will be step 2. Apply the substitution, and then convert to theta. So this whole integral is going to be in terms of theta now by the end of it. So we have this, right? And then we also know that root x squared plus 3 squared equals 3 secant theta. So we go ahead and write 3 secant theta on the bottom. Now dx we have to find from our substitution. So remember, we have this, right? So we'll copy that. So we have x equals 3 tangent theta. So that means dx equals 3 secant squared theta d theta. So that means that we can just go ahead and plug in the dx. So let's put this on a new line, and then dx is that. So now we have this as our simpler integral, and so some stuff will cancel out, right? That's usually the goal. And in this case, it'll cancel, so we just get secant theta d theta. So now, after we have applied our substitution, we're going to actually do the integral in theta, right? That was the whole idea. So we can see this integral is actually doable, and we're going to end up getting ln secant theta plus tangent theta. But now we're stuck in theta, right? So we have an answer, but it's still in terms of theta. We want to go back to x. So that's going to be our next step. Convert to x. And we are going to use triangles for that. So we know that x equals 3 tangent theta. That was our whole substitution, right? So let's rewrite that down here. So x equals 3 tangent theta. So that means that tangent theta is going to be x over 3. Great. So now is the part where we draw a triangle. So we know that you may have done this in pre-calculus when you were finding like inverse functions, something like that, or inverse trig functions. But you know that tangent theta is x over 3, and then you know that that whole thing is also going to be equal to the opposite over adjacent, right? That's the trig ratio. And then if you call this theta, so that theta is that theta, right? So the opposite is going to be x. So we just link it like this. So the opposite is going to be x, and then the adjacent is going to be 3. And then we solve for this side with Pythagorean theorem, and then we can figure out all the other trig ratios. So that side with Pythagorean theorem is going to end up being x squared plus 3 squared, right? So at this point, we've constructed our triangle, and now we can come up with the relevant things. So we want that in terms of x, right? ln secant plus tangent theta. We already know that tangent theta is x over 3. So this is going to be ln something plus x over 3. Now the secant theta is what we drew the triangle for. So we know that secant theta is equal to 1 over cosine theta. And then we know that the cosine theta, just reading off of this triangle, cosine is going to be adjacent over hypotenuse. So then we'll simplify, and I'll write the 3 squared as 9. So now this becomes our secant theta. So it's secant theta in terms of x. So now we can just plug this in to our ln, and after a bit of simplification, so we can write root x squared plus 9 and then plus x all over 3. We have basically arrived at our indefinite integral. And you could use log properties if you want to simplify this further. So this is how you attack indefinite integrals with trig sub. In another video, we will do the same integral, but we will have it be a definite integral. So we'll see what other things we need to consider for that. But until then, I will see you guys in the next video.